Okay, welcome everybody, and thank you, Dr. Haake, for joining us. I'll just say a couple of words, and first of all, express some appreciation for tuning in. And beauty of Zoom is that someone several hundred miles away can join us for a fairly informal conversation. And we try and do an educational session every month or so, but we have these dialogues every week, and you are all welcome to join us on Wednesday morning at 9 o'clock. Danelle Haake, and I hope pronounced your last name correctly.
It's actually Danielle Haake, but that's all right. I get both quite frequently.
Thank you. She began her career in ecology, developing water quality management plans for the state of Iowa, and has been a restoration ecologist with the Missouri Botanical Garden, where she reconstructed prairie and woodland habitats in urban environments. And she also began her doctoral studies at St. Louis University, studying the impact of road salt on ecosystems and urban streams. She's currently the Illinois River Watch Director and Stream Ecologist with the National Great Rivers Research and Education Center. And she's going to give a brief presentation on her research, and then we'll open it up to questions and answers. So, and feel free to add anything, Danelle, to my brief introduction.
Okay. I mean, that covers the general spectrum of my past. So yeah, I think that's a pretty good overview. While I'm talking, if you end up having kind of questions along the way, please feel free to interrupt. And if you end up doing that, you know, you can do that through the chat, or if you want to do that with the, you know, just by talking, that's fine. Either way is fine by me. Like you said, this is kind of somewhat informal. So thank you for inviting me to come speak with you about our use of road salt in the winter. My slides aren't working the way they're supposed to here, but I'm used to that happening for whatever reason. Okay, so the use of road salt to improve safety of travel following winter snow and ice storms is a relatively recent phenomenon. This is something that we started in the 1940s. Since that time, this practice has spread across most parts of the world where snow falls. Most of the salt that's used on our roads is sodium chloride, which is the same as table salt, or some other kind of chloride-based salt. There are other chemicals used, but those are the most common. But since it's sodium chloride and again, other chloride-based salts, I'll be talking about salt and chloride fairly interchangeably. The use of salt in the United States now exceeds 20 million tons per winter. And the purchase price for most cities that buy the salt in bulk is about $50 per ton. Of course, it fluctuates. But that means that we're making about a $1 billion annual investment in safe transportation in the United States. And that's just for the material. That's not for any application or anything like that. That's just the supplies of salt. So we put that salt down and it dissolved and it can do some fairly extensive damage to some of our infrastructure. And I just realized that my notes are different than what they used to be. Anyway, sorry, it's hard to get to my statistics when they've been switched out. All right, anyway, so basically, you know, the salt is corrosive to concrete, it is corrosive to metal, and so it does a lot of damage to our pavement, our infrastructure, and our vehicles. And that damage is estimated at anywhere between $5 and $10 billion per year. And so we're spending, you know, 5 to 10 times more to repair damage caused by the salt than we are spending in actually purchasing the salt that we're putting down. All right, so we put that salt down on the pavement, it dissolves into the snow melt, and the salty water then travels from our impervious paved surfaces, our sidewalks, parking lots, and roads into areas that have vegetation, and then also into storm drains. Salt at these concentrations is toxic to many plants, including grass, including street trees. So again, more money being spent to replace our green infrastructure. And it's also of concern in plant-based stormwater solutions like rain gardens. So the salty water runs off the pavement. And when it goes, rather than into grass, if it goes into the storm drains, then that water ends up in nearby streams. So these are freshwater streams, and the animals that live in these streams have adapted to freshwater conditions. Yet every winter, the aquatic life is exposed to highly concentrated salt from runoff, and this can create some fairly toxic conditions. Now, some of the salt doesn't end up in streams, some of it goes into groundwater. Both surface water and groundwater serve as our drinking water supplies. And so the increase in salt in these areas is raising a whole nother level of concern for human health and our drinking water safety. This is especially becoming a problem for people who live in places where they use local well water, but maybe the well water is coming from an area near highways. And then if those residents have underlying health conditions like heart disease, they're running into places where people can no longer drink their tap water. So that's a little bit of background on why road salt is of concern to a lot of people. Now we're going to briefly look at a few benchmarks that are going to be important in the coming slides. Naturally, streams have some chloride in them. The natural concentrations tend to be somewhere under 40 milligrams per liter. There are exceptions to this based on local geology, but for the most part, this is the case. Now, as far as water quality standards, every state sets their own standards for different water uses, and then these are approved by the US EPA. Now, the numbers I have here are Missouri, but most states are fairly similar numbers. So for many states, the drinking water, the chloride limit is 250 milligrams per liter. And then aquatic life threshold of what's safe for the animals living in the streams. They have a chronic toxicity level of about 230 milligrams per liter and an acute toxicity of 860 milligrams per liter. So talking about these two types of exposure, this is generally understood to be in terms of about 1 hour for acute toxicity and four days for chronic toxicity. So these are the concentrations that should be safe, or this like the maximum that should be safe for those animals for those durations. And then as just a point of reference, at the high end, seawater contains about 20,000 milligrams of chloride per liter. Right, so this graph is a little bit of a comparison of what chloride concentrations in streams looked like before 1940, before we started using road salt, and that's the dashed blue line there at the bottom. And then what concentrations look like today in streams that are somewhat impacted by road salt, and that's the orange line. So what we see are spikes in the winter. So these are associated with storm events. But if you notice, even in the summer and through the fall, what we're finding in streams now is higher than what we found historically. This is from the salt that's making its way into the shallow groundwater and then is being released year round into our streams. So one of the things that I did when I was working with the botanical garden is that I was working also with volunteers from the Missouri Stream Team, and they started helping me collect chloride readings in streams across the St. Louis area. So for those who aren't familiar with St. Louis, this is St. Louis County, and then this area is St. Louis City. So they helped me collect over 3,000 chloride readings in streams in St. Louis, beginning in 2012 and continuing on today. In a paper that's currently in review, we are relating these chloride readings to the biological health of the streams that are at these sites marked in black, and those are the little sub-watersheds for each of those sites. And the orange sites are additional locations where the volunteers were monitoring, but we didn't have enough biological data to really work towards drawing those conclusions. So the volunteers were taking grab samples, which is each just a snapshot in time. So the concentrations they were collecting may not have been the lowest concentrations and probably weren't the highest concentrations that were being experienced in the creeks. most of the volunteers wouldn't go out more than once a week. So they got one sample per week of what was in the stream. But even so, volunteers were often finding chloride to be over 1,000 milligrams per liter. So well above both drinking water and aquatic life standards. And we even had a reading of 8,000. So that's more than 10 times what's considered acutely toxic over a 1 hour period. So looking at those sites, I selected 15 of them that represented a range of chloride readings and then used data loggers for 2 winters to record conductivity at 15-minute intervals. So conductivity has a direct linear relationship with chloride. And so we were able to convert from one to the other. And the resulting data set for chloride in those 15 streams is shown here. These horizontal lines are the acute and chronic toxicity levels. And you can see that in all but 3 of the sites, so we've got these 2 here and this one over here, only those 3 sites stayed below the acute toxicity limit. So the dashed line here, whoops, can I go back? The dashed line is the top 75% of the data, or sorry, top 25% of the data. The blue box is the middle half of the data, and then the bottom quarter of the data are below down here. So this bar represents the highest concentration that we recorded. And you can see several sites had concentrations between 4,000 and 8,000 as their maximum. And one site was even more salty than seawater. So we clearly have a problem with high chloride in many streams in the St. Louis area. So salt accumulation in streams is a problem that needs to be solved with two things: resource use, so being better about how much we use, and stormwater management. A lot of stormwater management is done using solutions like rain gardens or stormwater detention basins. And those are basically, used to filter the water through a soil or a soil-like spongy medium. This water then enters groundwater or a stormwater system. So for nutrients, sediment, and other pollutants, these are fairly effective at removing the pollution. Unfortunately, the salt remains dissolved for the most part and passes through these filters, going directly into the streams. So really the only effective way to decrease the load of salt reaching our streams is to decrease the amount of salt that we're putting on the roads in the winter. One method that some cities and other municipalities are using to cut their salt use is the application of a salt brine. So what is brine? Brine is basically just salt water. So the practice of brining involves taking the same solid rock salt, dissolving it in water to create a 23% solution, and then spraying it on the road before the storm. So the idea is to prevent the ice and snow from binding with the pavement in the first place. And that way it doesn't require as much material because you're not trying to break a bond that already exists. Several economic and environmental benefits for brining. It can be done up to 2 days before a forecasted storm, allowing road crews to work during regular business hours and cutting overtime costs. According to studies that were done on interstate highways, you often get the same road clearing effect using half or less the amount of salt. So that reduces some of the negative consequences mentioned earlier, reducing the amount of salt that's put down. But there are potential drawbacks to the use of brine, particularly in areas like St. Louis, where it's difficult to predict the form that a winter storm might take. Now, this may not be as much of an issue for you, but in St. Louis, often a storm will begin as rain and then transition into snow or ice. Under these circumstances, if brine has been applied, then the rain will wash it from the pavement and the road crews will still need to return to spread the rock salt in addition. So that increased both the labor cost and the amount of salt used. So as I kind of mentioned, a lot of studies on the effectiveness of brining have been done on highways or else in parking lots. But there weren't really any studies that included real world applications of brine for residential areas or the use of the best management practice in multiple municipalities. So for part of my dissertation, I studied residential areas in 3 pairs of cities. Each city was selected to include, or each pair was selected to include one city that has a brining system, and this is the ones in dark blue, and city that does not have brining available, and that's light blue. The pairs were set up as neighboring cities to control as much as possible for the variability of weather as the storms pass the region. The pairs were also selected to minimize the differences in social and economic factors between the cities. Socioeconomic factors like city revenue, per capita income, and density of development could impact salt use within the city limits. Things like the city salt budget, resident expectations for road conditions, and the likelihood of residents using salt on their own private driveways and sidewalks. So the sites within these cities that we studied were selected to exclude areas that had commercial and industrial development. So this really is just looking at the residential application by either residents who live there, but the predominant source of salt is the what's applied by the cities. So for 2 winters, data loggers were deployed that estimated chloride concentrations and flow volume. Chloride concentrations were then combined with flow in order to determine the chloride load at 5-minute intervals, and then the chloride yield for each of the 9 storm events over the 2 winters of the study. Also, we had identified each of the drainage areas for each pipe using topographic coverages, and then the GIS information provided by the St. Louis Metropolitan Sewer District. And so the road area in each of these pipe sheds or watersheds was extracted so that we could determine the chloride yield as grams of salt per square meter of road for each storm. All right, so now we're getting to the results. Before I present these, I want to guide you through what you're going to see. On both axes, we're looking at the salt yield conveyed during one storm event measured in grams per square meter. On the x-axis is the amount from the city that has the brining technology, and on the y-axis is the salt from the city that did not have brine. And so every point that you see on the figure represents a pair of cities for one storm event. Now, any point that falls in the region above that 1-to-1 line is going to represent a pair for which, for that storm, the city that uses only rock salt used more salt than the city that uses brine. Any point on the 1-to-1 line is a storm in which both cities used the same amount of salt, and a point below the line is a pair in which the brining city actually ended up using more salt than the city that relies on rock salt alone. And what we found is that most of the points are above the 1-to-1 line. And so there's a significant linear relationship between the paired cities and their salt use. And this relationship is also significantly different or higher than the 1-to-1 line. So simply put, on average, cities that use brining technology used 45% less salt.
We have a question, Danelle.
Sure.
Danielle?
Yes.
Yeah, I was just curious. I thought from your description that you were measuring yield, but it sounds like you're talking about application rates, and I just wanted to make sure I was following correctly.
Right. So it is what I measured was in the pipe, the amount of salt that was in that storm water as it flowed through the system. But then, but I took that amount and, if based on the roadway area and the assumption that they applied the salt evenly on that pavement, this is the amount of the number of grams of chloride that they applied per square meter based on my calculations. So I'm basically kind of back calculating an application rate.
Gotcha. Thanks.
Sure. All right. Any other questions at this point on this? Because I'm going to kind of be moving a little forward here. Okay. So what would this kind of salt reduction, what does this look like in the real world? So to find out, we're going to do a little visualization. So imagine just a typical residential street. This is a street that was in our study area, about 7 meters wide. And then if you just think about a 1 meter stretch of that road. Now what we're going to do is spread one of these containers of salt over this short stretch of road. And then we're going to do that 4 more times. This is the amount of salt that the brining cities did not put on their roads that their neighbors did during the 9 storms over the course of 2 years. So extrapolated, this represents a savings of 1.5 tons of salt per lane mile per year. Now, according to FHA data, the state of Missouri has nearly 48,000 lane miles of urban roads that are classified as either minor arterial, collector, and local streets. So places where local municipalities are making the decisions of what to put on their roads. So the use of brining in all of these streets could cut salt use by 21,000 tons per year, cities and urban areas of Missouri. Now this would save that $50 per ton in purchasing and about $600 per year in infrastructure damage for a grand total of $46 million per year on urban streets of just Missouri. That's a pretty impressive savings. Now, most of the time, things that will save us money and keep infrastructure in better condition are bad for the environment, but this is actually not the case this time. So from the environmental perspective, about 4,000 gallons of water is protected by using brine on just this one short stretch of residential street in those 9 storms during 2 winters. And so doing the math to convert this into savings each year, we get about 77 billion gallons of water protected every year. This is the equivalent to a cube of water covering the area of 25 football fields with contaminated water 1 mile deep. I'm like trying to come up with some sort of image for that. That was the best I could come up with because it's just such a huge number. But this is what would be protected every year, again, just from urban areas of Missouri. Okay, so brining is just one tool, one of many tools in the salt reduction toolbox. And the toolbox needs to have a lot of tools because small differences in conditions like temperature can make a big difference in the effectiveness of any single tool. So all of the blue and white stuff in these photos is salt. And I hope we can agree that too much salt was used on the sidewalk and on this commercial driveway. So for me, step 1 is to use the right amount of salt. Don't over apply. According to most of what I read, there should be about 3 inches or about a finger length of visible space between grains of salt. That's the appropriate amount to use. Not that we expect anyone to go out and measure it, but we can certainly be doing better than we're doing right now. Another thing we can do, and anything that we put on roads will get washed into soil and streams. But we do have a little bit more and anything that we put in is going to have some sort of impact. But we do have a bit more flexibility on driveways and sidewalks. So individuals can put down sand and then sweep up the sand after everything melts and save it for the next storm. Or you can use things like bird seed, grass seed, leftover garden seed if you just need to improve traction a little bit. And something else we can do is monitor the impacts we're having on our local water resources. There's a lot of groups that monitor chloride, and a lot of them are just using these simple test strips. So besides the 3,000 plus data points from volunteers in the St. Louis area, there are other Missouri Stream Team volunteers who've been monitoring chloride. In my role as the director of Illinois River Watch, this October, we launched our own volunteer monitoring program called Winter Chloride Watchers in Illinois. And so now we have data that we're starting to accumulate from Illinois. Also, the Isaac Walton League has a winter salt watch program, and they've been doing similar monitoring for a few years now. Most of that is in the northeastern US, but I think that they do have programs open to volunteers nationwide. So those are just a few things that we can do. There are other chemicals also that people apply. There's, beet juice and other sugar-based substances that they're finding maybe it's a little bit better to mix a little bit of the salt and a little bit of the sugar as a different solution. But those are all options in the toolbox. And that's what I've got for you. So.
Awesome. Danielle, thank you so much. I'm sure there are some questions. I know I've got one. Kind of new to this area. What does it take to convert to some of these other alternatives like brine? And is that a heavy lift?
It depends on the creativity of your public works department. So of the 3 cities that I talked about for the study that I did, one of them built their own in-house system for about $20,000. Another city purchased a top of the line, state of the art that was several $100,000. So yeah, and kind of by the same token, that one of the local colleges around here, after learning about what I've been finding, they took like a water tank that they had lying around, some hose, bought a little bit of PVC, and for $200 they made their own equipment for the back of their truck. And because they have like a mile-long driveway for a field station that they operate, and so they ended up using only like 10% of the salt that they'd used in past years, and it only cost them $200 to make the system. So
what was that called? Isaac Walton
League.
Okay, thank you.
Yeah.
What about a small time, like a commercial setting? Is that easy to do it yourself, or does that require just a bulk tank, or what type of?
Yeah. I think, yeah, really the pieces of equipment that are needed are a tank with spray system, and then a system for mixing the brine, which I think it's possible to mix in the tank, especially if it's a fairly low use system. But most places that do more than just a little bit of brining, I'm fairly certain that they have like a separate mixing tank that they then pump into the distribution tank or the spray tank. Yeah, so yeah, commercial, I would love to see this put in place more commercially. And I think the biggest whole thing that's holding it back is fear of lawsuits. People put down way more salt on commercial properties than they need to, but if you don't have every square inch of your parking lot and sidewalk covered with salt, then you're going to get, someone's going to slip and they're going to sue you, or at least that's the fear. So I've actually, in many instances, felt like I was more likely to fall because of the slip hazard of the salt itself than slipping on ice. But it's a process, and I never remember. I think it's New Hampshire that has one of the states out there. They actually have basically a class, and if you go through the class on how to properly apply salt, then you are, people can still sue you, but they won't win, basically. That like, no, I applied it properly according to state guidelines that say this is what we're supposed to do. So it's, protection against loss of a lawsuit for the most part. I mean, people can sue people for anything they want, really, but.
So I had a question about other chemicals. You mentioned the beet juice, and I am aware that Michigan State University tried the beet juice for a while, but I think they gave it up. My understanding was that it was because of the excess organic biological oxygen demand that it ended up dumping into both the local lawn, but also into the river. But what about, for instance, other salts that break down, for instance, sodium bicarbonate? Is it just that those things are so much more expensive that nobody ever wants to consider them on a large scale?
I'm sure that cost has a lot to do with it. And that aspect of it is not really within my area of expertise, but I mean, there's several different chloride salts that are used. And I think, and based on the temperatures at which they work, like sodium chloride is only effective down to say 20 degrees. And then after that, you have to start using either applying a much higher rate or using, I think maybe calcium chloride is the next one that they move to, something like that. So, and that's why there's, so many different tools in the toolbox, so to speak. I'm not sure about non-chloride salts. I know there are a couple of other non-chloride chemicals, but really anything that we're putting down on the roads is going to have some sort of environmental consequence. Like you mentioned with using of beet juice or any other kind of sugar-based organic compound, you're going to have the oxygen demand in the streams from that. Any salt is going to have some sort of toxicity associated with it. It's just a matter, and I mean, salt is a natural chemical in the environment. It's just that we're overloading it and having consequences from that.
Yeah, I mean, there are salts that ultimately can evaporate if you go to high enough temperatures, like where they would, ammonium salts, for example, in the summer, you could imagine those things actually leaving. But yeah.
But nitrate is another kind of chemical that people, we have so much ammonia or, various, nitrogen-based compounds in our streams that, fertilizers and everything else. So I don't know if that would end up being a helpful addition or not, or if we would just be having more summer eutrophication at that point.
So the other question is, what about the engineering of road surfaces in themselves? So around here, what they do is they, as a bicyclist, this annoys me, but they use what they call chip sealing, which creates a pretty rough road surface. They basically lay down asphalt, and then not too long after that, they cover it with loose sort of pea gravel. And I think my understanding is the idea is that the use of the road by cars, eventually sort of grinds that gravel into the asphalt surface, but it makes a fairly rough surface. And I was just wondering, is there, how much, if you have a naturally rough surface, how much can you sort of save on the need to either to apply anything to improve traction, that in terms of shedding water, in terms of building up ice, all those questions.
Right.
I was just curious.
Yeah, I mean, again, not quite my area of expertise, but just kind of my perspective on it is that would definitely help in rainfall situations and but I mean, depending on how much snow and ice you're getting, it might be helpful, but there's also the question of when you plow that, is the plow going to be knocking off a bunch of those little tips on the chip seal equipment? And so that would, may be effective for a shorter time than we'd like. In the St. Louis area, what we deal with most frequently is snow that immediately gets compacted by wheels and turned into ice. So, it doesn't take a whole lot of ice to make roads kind of treacherous in a lot of places. So,
yeah.
But the type of precipitation can make such a huge difference. If you get kind of a light fluffy snow versus like that dry powdery kind that you can just, if you keep people off of it for a couple hours, it'll probably just blow away, drift somewhere else. But
right.
What other questions do people have? Hey, not to put you on the spot, Rob, but we have one of our building and grounds directors on the line. And Rob, do you anything come to mind that say you like the idea of putting some brine down or experimenting with brine? What are some of the barriers that you might encounter with the public or with your workers?
Really, it's just changing over all your equipment. I spoke with Michigan State about their brine tank probably 5 years ago, and it was quite the amount of money that they had to put in just to get it started. And then storage of the brine tank, because I got it indoors. It's really the initial infrastructure cost.
Right. And there might be grants available for something like that. I'm not sure, or special loans or something like that. But yeah, it is possible to in the city that that did a lot of it themselves and put together their system for $20,000, it paid for itself in the first year. So if you have a group of officials in charge of your budget who can recognize the fact that, you know, if you end up reducing your salt use by 50% and reducing your overtime costs for winter salt application, if you do a lot of application at night, you know, if you can tell them, look, this should have it, you know, some places it's paid itself off in more like 10 years. That's, you know, 5 to 10 years is probably a more realistic payoff. But it does save money.
Yeah, and we're on the small scale. I mean, we really take care of just our own buildings. We don't take care of the streets or anything else. So, I mean, we're right around maybe 100 ton. So about $6,000 a year is my rough guess on what we spend on salt.
Right. If you're interested, I can connect you with the people at Washington University in St. Louis. They're the ones that put together a system with stuff they had laying around, and they did it for about $200. So
yeah, well, I mean, I'm that type that I could do that, but I'm not sure that I got the capabilities underneath me. How's that sound?
right.
Yeah, I'm
But
particularly
yeah, please
interested-
send that along if you have a chance to know, Danielle.
Sure.
I'm particularly interested in the application of our pathway system. And my understanding from our Director of Public Works is that the equipment that we currently use to clear snow doesn't have the capability for salt or brine at the moment. But we did recently get a study showing the cost and benefits of converting large parts of our vehicle fleet to electric. And it occurs to me that that might be the moment when we might be able to make that jump. When as we replace equipment, if we look at equipment that's capable of brining as well as rock salt, that might get us where we want to be.
Right. Yeah, just planning ahead as you're finding specifications for new vehicles, that would absolutely could be key. I
noticed on your background that you've done a lot of work with citizen scientists, and a lot of what we're talking about is, you know, how do we engage our communities and our youth, our residents in some of these solutions that we're suggesting. I don't know if we have something equivalent to citizen scientists. I know we do have some volunteer stream monitoring that goes on, but
well, that's citizen science, so yeah.
do you have a large crew that you work with that on an ongoing basis, and do you direct them, or is that directed through another agency? So the Illinois River Watch program is kind of the statewide citizen science water monitoring organization. And we've been around for 25 years. I've been part of the program for about 2 years now. And most of the monitoring that our volunteers do is to go into the streams once a year. Although I've upped it and encouraged that if they're interested, they can definitely go a second time. But have them going out in the late spring and early summer to do water monitoring, looking at the aquatic invertebrates, and then just kind of doing a visual assessment of the habitat. So that's kind of our primary program that's been around, again, for 25 years. This year, I added the chloride monitoring program, and I've trained about 60 people. It was a 1-hour online training session. Trained about 60, and I have about 20 or 25 of them who I've actually sent equipment to, so basically sending little bottles of test strips here. And they go out and you know, once a week, once a month, whatever fits best for their schedule. And they do their monitoring that way. Every spring we have training sessions all across the state to teach people how to do the invertebrate monitoring. And then we also have some overachievers in the program who do additional types of monitoring. We have a few data loggers for temperature that we can send out to volunteers, and they put those in their streams. We have some volunteers who have been doing freshwater mussel monitoring. There's a group that's been doing that for 10 years, and just this past year we got a grant for them
so that they can, they're now actually doing tagging of the mussels so that we can do like basically a long-term mark recapture study on freshwater mussels. So citizen scientists that, once they get involved, they'll know what their level of interest is. If they like it, and then, you'll find a few of the excited ones who are like, oh, that's really cool, but can we also do this? And basically, I was one of those volunteers. Yes, I was bachelor's degree in biology, but while I was doing that, I found out about Missouri Stream Team, and I've been participating in Missouri Stream Team ever since. So yes, I'm a scientist, but I'm also a citizen scientist who goes out and uses these kind of simpler methods than you would normally do, in a scientific lab, but it's enough to give you some information and background and provide educational opportunities for other people.
Thanks.
Yeah.
What other questions do people have or observations?
I was just wondering, it didn't sound like you had addressed any issues with the water usage with the brining technology. So I'm assuming that that's really not an issue.
As far as like the water used to create the brine, or?
Well, along the continuum, yeah. What is the source of the water, and was that a significant cost in the process of brining?
Not that I'm aware of. In the people that I've talked to, they haven't ever expressed any concerns about that. And really, if needed, it doesn't have to be tap water. If they have a rainwater harvesting system that's set up on the salt dome, then, or they could just put that into the tank, and then when they're ready, add the salt to it, because the water is just going to go on the road anyway. It doesn't need to be any specific.
And what volume of water is required for?
It depends on how many roads you're covering.
Right.
I don't really have I don't have a great feel for that, unfortunately.
Hmm.
Yeah. But something else that the public works director and the city that I happen to live in, that is part of the study area, he did mention that not only are they able to put down the salt ahead of time and not have the overtime hours, but it actually doesn't take as many trips with the trucks to cover all of the roads, because you're only doing a 23% salt solution, you're only using a quarter of the amount of salt. So even though there's a lot of water in with it, they don't need the trucks can go further before they have to reload, basically.
Okay,
that's something I always forget about.
Thank you, Bill, for posting that link on stream monitoring. Is there a similar type of a training you mentioned in New Hampshire that would reduce lawsuits for this application of brine, or does that apply to brine as well as regular rock salt?
I think it's just salt use in general, and yeah, I'm sure that I hope it includes brine, but I haven't really looked in depth into that program.
Okay.
So
great. I saw that you're also interested in microplastics, and we had a presentation on that last year. So maybe we can connect about that another time, but I really appreciate you being here, Danelle. And any other parting comments or questions before we wrap up? Thank you all for tuning in. And Danelle, if you do have any of those other conversion for costs from that university, I think that would be interesting. And then I've got Danelle's email if anyone thinks of additional questions they'd like to share. But we really appreciate your generosity of time and all of you for sticking around for this conversation. Hopefully we'll connect again, and appreciate everything.
Actually, I just happened to find the article from a couple of years ago about the use of brine, and it has the name of the people involved. I don't actually know that I have their email handy or anything, but this will get you some more information on it.
Fantastic.
Thank you, Danielle. That was fascinating.
Thank you.
Well,
We'll see you on down the road, so to speak.
sounds
All
good.
right.
Thank you.
And tune in
Thank
again
you.
any Wednesday morning at 8 a.m. for you.
8 a.m.
Take care.
Bye.
All right.
Thanks again.
Bye-bye.